Welcome back to the DemystifySci podcast. I'm Anastasia.
I'm Shiloh.
And this is the place where we search for the theories that are going to change the world. And as you know, one of the things that we spend a lot of time talking about is the nature of quantum physics. We really want to understand what is behind the mathematics. And over the course of this show, we've probably had easily more than 100 conversations with quantum physicists. And for the most part, people come down to the fact that, well, the math is what reality is. But there's a strong vocal contingent of people who believe that behind the math, there is actually some kind of reality. And our guest today, Dr. Chantal Roth, is one of those people. She is a champion of a theory called the elastic ether theory that says that there is actually some kind of physical substance that pervades the universe that is responsible for electricity, magnetism, light, charge, gravity, all of the things that quantum physics says are field-based phenomena that kind of emerge out of the math, Chantal says can be explained by there being this elastic substance that fills the universe. We already had one conversation with her about the nature of this substance and the broad strokes of her theory, and this is the conversation where we dig into the details. How does the theory actually explain these phenomena that, up until this point, everywhere else in the world, have only been described quantitatively?
If you, like Chantal, have a theory of how something in the world works, you could sign up for our segment called Paradigm Drift, which happens once a month. You get a chance to put your name in a hat and maybe get the opportunity to present your idea in a minute or less. I would love to see you there. You can learn more about it at DemystifySci.com.
If you'd like to support the podcast because you listen to it and you think that what we do here is interesting and engaging and you want to see more of it, then come on over to patreon.com/DemystifySci. For 75 cents a week, you can sign up to support us so that we can continue improving the quality of this presentation. We have big plans for everything from in-person interviews to yearly events to maybe even being able to hire an editor so that we can record in higher quality. We have lots of ideas. But if you've already joined the Patreon and you are kind of like, I wonder what else I can do, well, think no more. We have made 2 separate hoodie designs. They're down in the description. One is Shiloh's, one is mine. So we have a small and quiet competition going about who sells more hoodies. But then we also have a mutual project. We have a band. And the band is called Secretary of Nature. And this record is so hard to hold. I don't understand why it's so hard. All right, here. Yes, this is the record. It's called Everything Is So Good Here, and it's 2 sides of vinyl, 6 songs. They're kind of psychedelic, they're kind of rock and roll. They're lyrical songs about the weird experience that it is being alive on this rock in the middle of nowhere. People have been saying that we should share our music a little bit more, and so what we've started to do is the introduction to the episode is a little selection of a song off the album. And so enjoy that just before we get to our conversation with Dr. Chantal Roth about the true nature of the elastic ether and how it explains the fundamental phenomena of nature. We have that mass will affect the ether, but if we don't have a sense of what gives rise to mass, then how can we make any conclusion?
Inertial mass versus gravitational mass, right? And
oh boy.
If you consider both as stored elastic energy, if you think of it both, if mass is nothing else than waves, like the electron, the spherical harmonics and all that, right? It's just a wave, which is really stored elastic energy. This wave wiggling around,
So it's like displacement of subunits, like cyclic displacement of subunits. Is that what you mean by it?
Yeah, exactly. Like a wobbling cello, right? It's basically a wobbling cello. If there was a god, he would, hit that cello and then he would start to wobble, and that's it, basically. So if you consider mass as being stored elastic energy, so that's within a volume you have. If you imagine these springs, and if you look at each point, what it's doing, it could wobble this way or that way, and there's different oscillations. Like each grid point, it might just go up and down. It might go in a circle. It might, form an 8. There's different combinations of what each grid point can do. And if you just watch what one grid point is doing, it's like a pendulum. So you either have kinetic energy as it's going fast, and then it's reversing right, up and down. So you have kinetic component. You have compression. If you have 2 points approaching, you have compression. You have twist. This is all, basically expressed as, you can imagine, as stored elastic energy. And if you want to accelerate mass, so if you want to basically move this wave packet somewhere else, you have to apply extra shear and compression to move this stored elastic energy. And the more you have of it, the more you're going to have to push. So this is basically what mass is, right? It's the resistance of these stored elastic energy to actually move somewhere else.
Is that a thing that materials do, though? Like, do you have these standing systems that can move around, these standing harmonic nodes that just move around inside of materials, in terms of phonons or something that's analogous?
That's the question. Yeah. So phonons, sometimes they're called particles of heat also, right? And how they're used in studies where you check how heat moves around in like metals and stuff. So
we actually had a really interesting conversation with one of our friends, Michael Hughes, who works on the biochemistry of water. Okay. And he had this entire model, which actually was similar to this in some sense, where you have signals that can travel through water faster than diffusion, because the thing that's traveling is not the water molecule. The thing that's traveling is this geometric organization of water molecules that is able to be passed. The signal is the organization, not a block of water molecules that are moving together. And so as that information moves across a cell or across a test tube, it moves significantly faster than diffusion. Right. And so that seems to be similar to what's happening here, right? Because we're talking about some kind of organized state, and the thing that's moving is the organized state, not this. It's not the ether that's moving.
Oh, no.
It's the configuration of the ether.
Average. So the ether could wobble, but it will always be play on the average over time. It will not be moving anywhere, right? So that's why it's an elastic solid. But each point can wobble this way or that way. And temporarily, you have this small, like when you zoom in, each gripper can move, but it's still stationary overall, right? On average.
And
so then the density has to be the same, right? So your model relies on the density being constant, essentially, of the subunits.
Not necessarily. I mean, I remember Robert Close was writing about this at some point, and he was arguing that when you have more mass, means more wobble motion, then it pulls basically on the ether, so you would get overall an average increased density. Now, I don't know, his paper is very mathematical, so I'm not quite sure, but that's something, I could actually ask him. Yeah.
Yeah, I guess I'm just thinking like, okay, let's say you have like a wave, a little harmonic wave, like I just focus sound inside of a piece of jello and I get this thing that kind of even looks like an atom, like a spherical harmonic inside of it. If I want that to go somewhere else, I have to drive it from external drive, my speaker or whatever has to point somewhere else, right?
Right.
And so the source of the wave, in this case, what we're calling like the atom, the vibrational mode, the standing wave, is externally determined by the drive, which is being focused from an external locus. So, it's almost like the thing itself, the atom in this case, inside of the jello, the analogous atom, is it's not that it's moving so much as that the external drive is focusing it somewhere else along the way.
What you mean. Yeah.
And so when we, I don't know, this is as close as I can get to understanding this model that you're pointing at.
It depends if the material is purely linear or if there's some non-linear effects as well. So Robert Close, for instance, argues that the ether is not perfectly linear. And so he argues that because there's some non-linearity, you can actually have soliton waves that are stable on their own. They won't disperse, right? And again, I don't know if that can be proven. Again, this needs more research, but either it's what you're saying, that you could imagine the whole universe is just wobbling and it's just, everywhere basically, and it's just matter. It just happens to be, some standing waves that form we are just lucky, right? But it could also be that they're soliton waves, because if there's some nonlinear effects, you can actually have stable soliton waves that don't disperse.
I'll just try to. Okay, I'll try to wrap my head around this for a second.
Well, what's tripping you up? I think we can sort this
Just
out.
these autonomous standing waves inside of a jello that are moving around by themselves. I'm having a hard time coming up with a physical analog for such a thing without being driven by.
There's like soliton waves in water, right? You can have like a single wave that moves.
Yeah, maybe we can talk a little bit more about soliton waves. Like, what are soliton waves, and what do they tell us about this model of the universe?
They're like self-sustaining waves that don't disperse. So if you just take some material and you wiggle it, the wave will go, the energy will spread on all sides and it will be gone, basically, right? So it won't stay stable. But there are like different ways you can create waves that stay stable. They stay compact as a unit. They don't get wider. They just stay the way they are. And you can
without being driven? Like without being driven externally?
Yeah, basically, yeah.
Mm-hmm. Huh.
Is this,
what's an example of
that? Is
that?
this theoretical or is this
No, there's practical, but I would have to look it up also. I haven't spent that much time on this, but I can send you links for sure.
Okay, excellent. Shiloh, it looks like Shiloh's on the
I'll write it down, okay?
On the trail.
I'll definitely soliton waves. And I know Robert Close has written more about this, so there are examples of soliton waves, yeah.
But so I guess what the way that I see it is that there is this, we don't live in an empty universe. And so earlier I was like, okay, so you can imagine you begin with a totally empty block of jello, and then you drive it externally and you drive it at just the right frequency to create one single atom, which is, the mass of a hydrogen.
Yeah.
That's obviously not the universe in which we live. We live in a universe where we're surrounded by material that is constantly in vibratory motion. And the vibratory motion of one object affects the vibratory motion of all of the objects next to it. And that goes all the way up and it goes all the way down. And so the drive does not necessarily have to be external to the system.
Exactly. The universe, if you assume the whole universe doesn't lose energy overall, then once you have waves in there, they will stay in there forever, right? They can't go anywhere. So
yeah, exactly. Yeah. And so what I see you building is I see you building this like vibratory model of the universe where you say that this all must be some kind of reversible deformation of an elastic substrate. Yes. And the various deformations of the substrate produce the various effects. And so we've done light, which is, well, actually, have we done light to our satisfaction? In this model, is light just some kind of transverse deformation of the ether?
Yeah, I think so. I mean, we can also talk about electromagnetism at some point. Maybe we can talk about this briefly, if you like. So, since light is an electromagnetic wave, right? One interesting thing is that actually when Maxwell developed it, he also looked at the mechanical model, right? He had these wheels actually rotating, which was really, of course, the analogy that didn't work that well. But so when we start to describe waves, for instance, magnetism, right? We have magnetism B is the curl of A. So the question is, what is A in this model of the elastic solid, right? So the most natural thing to start with is, imagine we have, again, this elastic solid. And let's just keep the refractive index the same. And we have grid points everywhere. So we just draw a grid. Is to look at the displacement. At every point, we can, at any point in any time, we describe the elastic solid as, are the grid points at rest or are they displaced a little bit? Are they, the x-coordinate is a little off and then it goes back, for instance. So we look at the whole displacement. And then, of course, in elastic solid, you could have both longitudinal waves and you could have transverse waves, right? But in the case of electromagnetism, we just look at the transverse part. And thanks to the Helmholtz decomposition, we can't do that. So we can't just focus on the transverse part. The next thing we might look at is just displacement alone is not very useful. How about the derivative, right? So we look at velocity. We look at, well, how fast is each point moving everywhere and every point. So that's the next thing. And I would say in that model, what matches really well is when we say the A, so the curl of A is actually velocity. And I think it's what also Maxwell had originally. So, and then what is the curl of A? So what is the magnet? What is B? The magnetic field is basically when we have a circular, a twist, a curl, a vorticity of the velocity, angular momentum density, that kind of thing. So then that's what B is. So imagine like a hula hoop. If you do like you're in the pudding, in the cello, and you're kind of doing a hula hoop, right? It wouldn't break the cello. So even though you introduce this wobble motion, so the whole cello pudding is gonna start to wobble in a circular fashion, but you're not breaking it. So that would basically mean you have each point in that cello would have a velocity, right? It's just going around in circles. And the curl of this, there is a curl because it's going in circles, and then you would have a magnetic field going upwards in that case if you have the movement going, counterclockwise.
Electric fields, not right? Because we're talking about the magnetic field. The hula hoop is the magnetic field, and the electric field would be going upwards, right?
So the hula hoop, basically the electric field has two parts, and we can map it to displacement. So the E would basically be the displacement, and there's also an acceleration part. But basically, the E would be related to the displacement, and the B is the curl of the velocity. That's the B, the magnetic field. Mm-hmm. So when you have something circular, when you ever have a wobble motion in the elastic solid, that would create a B, basically.
Yeah. But you were saying that from the circular wobble, you were saying that the magnetic field points upwards off of the circular wobble.
The magnetic. If you would draw the arrow, you would basically with the right-hand rule, the way you would draw it is upwards, I think.
I thought that the right-hand rule was that the curl of the magnetic field is your fingers, so that's the B, and then the E is the thumb.
She's talking about J, the displacement currents, I think.
I'm so confused.
Are you talking about the displacement currents?
I'm just talking about, B as the curl of A, magnetic field B. So it's just basically when you have velocity and you're going in a circle, the place where the magnetic field points, the way you draw it is basically you have this plane of the velocity, and then it's basically pointing upwards.
Let's imagine that there's a current carrying wire, right? So we have a current that's running along the wire, and then we have the magnetic field that's curling around the wire, because this is also the E cross B relationship,
and
right?
Well, if you have with charges, so let's see, how does it work again? When you have the electrons going in a circular way, then you have this magnetic field going like this, right?
Mm-hmm.
And you draw the magnetic field. So it's rectangle. So it's basically when the electrons go around the wire like this, you have the magnetic field. If you draw like all the magnetic field lines, it would look like this.
Like a torus, like a magnet.
Yeah.
But the magnetic field line around a wire is circular.
She's got a circular wire.
Yeah, wait.
She's using a circular wire.
Are you using a circular wire for this example, or is it just?
It doesn't matter. No,
Well, it does matter. Yeah. It does matter, okay, because if you have a straight line wire, then your current goes up in this direction, and your magnetic field curves according to where your fingers point, and so you have a circular magnetic field around the wire, right? Right. And so this toroid, the toroidal thing. I'm confused by the toroid.
Wire. Yes.
I see. Okay.
Yeah. The main point is we can map the electromagnetic field to the elastic solid. It's the same. No, we can have a mechanical picture of this where B is related to how these grid points in the elastic solid move around, how they oscillate. We can then attach the E and B arrows basically to them by looking at how they move, right?
So the grid points actually move around, or is it the stresses that they're experiencing?
How they oscillate, basically how it oscillates.
So the little points are moving around. The little grid points are actually moving?
They are stationary on average, but when you have a light wave, for instance, passing through, at that point, let's say grid point 5 would go up and down, and then the next one would go up and down, and so on, until the light wave is passed, then it would be at rest again. So the grid points will not go with the light wave. They would just intermittently oscillate as the light wave is going through.
I think that the thing that we're stuck on is that while that works for the passing like wave of the photon, where you have these magnetic and electric fields that are orthogonal to one another and orthogonal to the path of the light travel, you're then stuck with something of, okay, so if you have a current carrying wire, you have this circular field around it, which seems to, and if you put a charge in that field,
of course,
then it rotates constantly.
Okay, charge is a big topic. So if I'm skipping a lot of things, but okay, we can go with charge. Charge is interesting because charge is a big topic. Okay, so we have to figure out like what is charge, right? And charge has a lot of interesting properties. First of all, there are only two types, plus and minus. And then it's basically spherically symmetrical. We have the Gauss law, which means it's related to, the charge density is related to the divergence of the displacement. We have things like if we did a simulation of charge and if we reverse the simulation in time, it would be like plus would stay plus and minus would stay minus, right? Interesting also the mirror image. So if it did, have a simulation of charge and we have a mirror image, it would always also be the same charge. So a plus stays plus. We have charge conservation. So you cannot just create a positive charge. You have to create a positive and a negative charge at the same time. And also the total net charge in the universe, it's claimed to be zero. So we don't know for sure, but as far as we can tell. So do you have any ideas? I mean, I have looked at 6 different models of charge, and one of them is kind of the winner. What do you think charge is? If you assume the universe is an elastic solid, how would you model? You have this one charge here. I'm just curious what your thought is, if you have thought about this.
Well, I think that it is a relationship between two atoms of different states of motion. I guess that's the simplest place I would start, is that, first of all, every place that we see charge in all of these systems, looking back over 300 years of experimentation, involves atoms. So I kind of would start there as it being an atomic phenomenon, where the atoms are doing something to each other and they're in different states of motion and they're transmitting some imbalance in that motion between one another. And so I would see it as something like an overdriven state versus an underdriven state, where the electron is a particular harmonic pattern of motion in the surface materials motion of an atom. And so you have essentially overdriven and underdriven surface motions being...
What do you mean, underdriven and overdriven?
I mean that there's more zip in the materials are still doing the same motion. So that spin 1/2 motion of the electron surface of the atom is still the same. It's got the same pattern of motion, but there's more material in motion in one versus the other. And since the atoms probably have the same amount of material, if they're made out of the same stuff, there's more motion. It has more freneticism to it.
Well, so the way that I see it is, can I add a little bit to that? Okay, so we know that every single mass, every single object has some kind of fundamental frequency. Like if you hit a tuning fork against the wall, it vibrates at a clean tone. But if you look, you can still see that there's these little bumps to it as you move away from the fundamental harmonic. I think atoms are similar. And so when you have a neutral atom, you have it vibrating at its natural frequency. And then as you add more motion into this atom, you shift it away.
As you drive it.
As you drive it. You either shift it into a higher frequency vibration away from its fundamental, or you shift it to a lower frequency vibration away from its fundamental. And that vibration comes in units of spin 1/2, because that is the angular momentum quantity that you can add to this system for whatever reason.
Well, the reason is that when you drive something, just like the Chladni plate, right, you're going to drive it by discrete, like its shape change is discrete. Therefore, the quantity of energy needed to be put into it is discrete as well.
Yeah, I think the Chladni plate's a great example here, right? So it's like the reason that charge is quantized is for the same reason that the Chladni plate is quantized. If you vibrate it at some frequency, and then you start to increase that frequency, you just get chaos for a while until you get to the next frequency that gives you some kind of harmonic.
I.e. the next the next charged state, the next ion level, or the next charged state. Another electron is glommed on.
Yeah, exactly. And so I like to think about this in terms of like a battery that's connected by a wire between the negative and the positive terminal. So, and there's nothing else in the system. You don't have a light bulb. It's just, you're just draining the battery by connecting the positive and the negative terminals. What's actually happening inside the battery is that you have two chambers, and both chambers are connected to these electrodes. So you have a cathode and an anode.
Mm-hmm.
And at the negative terminal of the battery, you have a chemical reaction that is spontaneous. It is a spontaneous reaction that causes it to generate an excess charge. Right, so you have an oxidation reaction, which is that you lose electrons. But what that really says is that the oxidation reaction has powered the zinc, which is usually what's at the anode of a lead acid battery or an alkaline battery. You've pushed the zinc through this reaction with oxygen into kind of a more frenetic state. And when you connect the wire from this negative terminal that has this excess of motion to the positive terminal, what happens is that you've connected it to a sink for this same frenetic motion, because there is a manganese oxide reaction at the positive terminal of the battery, but it is energetically unfavorable. It will never occur without a little bump. And so when you connect the two terminals of the battery, what you've done is the motion, the frenetic motion that's excessive on this spontaneous reaction of the zinc, is passed into the wire. And then all of the atoms in the wire are basically collecting this motion from the zinc. And there's so much zinc in the battery that it can saturate the wire. And at the other end of the wire, you have this manganese reduction reaction, which is the gain of electrons. And what that really is that is a sink for the motion, where you've created an excess of motion at the negative terminal.
It's very similar to like heat or something like that. It's very similar because people used to think of heat as these little particle thingies too, right? They thought of it as like this fluid, like very similar to the way that most textbooks talk about electricity. But I think that, and I don't think we're alone in this, but a lot of people are imagining it really as the motion of this material that's being dissipated, much in the same way that we understand heat is this molecular motion. This is really some sort of motion to do with the surface motion of the atoms themselves.
And so this is what's really crazy about this, is that when I was doing my graduate work, I did a lot of electrochemistry. And it drove me crazy because the electrochemist, you would imagine that if charge was some immutable substance, like if charge was the same thing as like a hydrogen, that something would always, and so hydrogen always has the same mass, right?
Yeah.
And so you would expect that some item would always have the same charge. Like if you had an atom and you charged it. But as you change the material properties of your electrical system, as you change the material of your electrode, as you change your electrolyte, as you change the conditions where you're studying your molecule, its charge also changes. And so it's a relative measure. It's basically like charge does not exist as this idealized little blip that you can place into the world. It is always decided by the relative behavior of the molecules inside of your system and how they're capable of exchanging this sort of elastic energy between each other.
Interesting.
That's a very long answer to what should be a simple question. I'm sorry.
Yeah, I guess what I was trying to ask is, if you zoom into the ether, right, into the elastic solid, very deep down, like how do we model charge, right? Is it a wave shape or is it some static pattern? That's the question. And different people have different answers. It's very interesting how many different models there are. Like some, for instance, I know Jeff Yee, he has the model that charge ultimately is some kind of, he thinks it's a spherical standing wave. I don't think it works because the way he models it, for instance, is that plus charge and minus charge would depend on the phase of the wave. So that can't really work well. And also, if it's oscillating, the problem is when you model this, when you have, for instance, we know that when we have a moving charge, just a simple moving charge in a wire, it creates the magnetic field around it, right? And we have already described the magnetic field as being the curl of the velocity. So whatever charge is, when you move this thing, it has to be able to produce this curl based on our definition of what we think the ether is, what we think E is, and so on. So that doesn't work out. So charge can't be a spherical standing wave, as an example. Another idea, I know someone else, they have the idea that it's some kind of other type of oscillation, like a trefoil, but it has the same problem, really, because in that model, the orientation of this wobble motion would determine plus versus minus charge. But we already said, like, if you run the simulation backwards, it should be the same charge. So that doesn't work either. If you have a mirror image, you would flip it, but that is ruled out as well. And there are many models like this that are ruled out because of this.
Which is why I think that... Oh, yeah, go ahead.
Oh, well, the simplest one is basically... It's basically already says it in the Gauss law, right? So you have the divergence of E. So now E has two parts, but if we look at E as displacement, and we are saying there is a divergence of displacement, so like a source in the sink, basically, right, of displacement, then what charge means in this case is just...
Hey guys, remember, we can't do this program without your support. We are not sponsored by anybody. We're not selling you anything we didn't make, but we need you to come over and check out how you can get involved in supporting the program at patreon.com/DemystifySci.
Have some places where there's a little bit more volume, more ether, let's say. So, and you could do this by basically, imagine you had a cello, and let's say we make everything of tapioca pieces because it's easier to see. And you take one of those tapioca pieces and you just shift it over just one grid distance over, and you can keep pushing it like a Newton's cradle. So then what you end up with, you have then one place that is essentially, quote, almost like missing a piece. So you have then the divergence of E pointing inwards because you have a slightly reduced volume. So it looks like a sink. And then on the other end, where you pushed and you kept pushing it, you have now a little bit of increased volume. So you have a source, basically the arrows pointing outwards, where you have displacement going outwards. And with this simple model, you get the same charge when you reverse time. Mirror image stays the same. You get automatic charge conservation. You can never create just positive or negative. It's always connected. Also, when you imagine this defect moving, you automatically get the curl. So when you have this moving in a wire, for instance, you would get the correct magnetic field based on the plus or minus charge. Now, of course, I don't know if this is correct, but at least this model works really well because it's super easy and it fulfills all the properties that I know, at least.
Do you think that spin 1/2 is important for charge?
I think spin 1/2 is separate from charge. So spin 1/2 is really interesting because, and I've puzzled for this for a long time, because spin 1/2, right, it has these really interesting properties that it is a source really of magnetism. That's one interesting property. It is a source, it has angular momentum, intrinsic angular momentum. So it gives the electron, not the orbital angular momentum, but it's the intrinsic angular momentum. And the other aspect is, which is really weird, is that you have this 720-degree rotation. So, I mean, I don't know. So when you have a cup like this, right, when you rotate an object around once by 360 degrees, it's back where it started, right? And so the weird thing is for spin 1/2, you need 2 turns for it to get back to where it started. And for me, when I first learned about the elastic solid model, like, that was the killer. I'm like, if we cannot explain this in the elastic solid, then that's it. There's a problem. So I was really, I wrote a lot of simulations on this, and it's actually really easy once you see it. I don't know if you have done this before, but it's like a little puzzle, right? So basically what we want to do, if we want to show that this works in the elastic solid, is, since the elastic solid, it shouldn't break, right? We can't rip the jello apart. It needs to be intact the whole time. We need to find a way to actually rotate this cup in such a way so it doesn't break the elastic solid. You need 2 turns for it to get back to where it started. It needs to have angular momentum. And you should be able to do this continuously. And the trick, so I don't know if you have tried this, but the puzzle is you need to hold this cup without letting go and try to do this. You think you can do it?
Well, isn't this the belt trick?
Yeah, exactly.
Okay.
Because if I start to rotate, I get stuck really quickly because my arm is in the way, and so I have to move my arm out of the way. So what I do, I have to move my arm upwards, and you will see now I've gone around once already. I've rotated 360 degrees, but my arm is not back where it started, right? It's not, it's totally different now. I have to do this again. I move my arm downwards, do a second rotation, and now I'm back where I started. Which is really interesting because you can actually do and remember, I did a rotation, so it did rotate. So there is angular momentum. Even if you imagine this was a really heavy bowling ball, right? And you keep doing this, you can do this continuously. And you actually have intrinsic angular momentum. And also what you can do, you can actually connect this to the living room anywhere in your room. It will still work. It will not tangle up. It will not tangle up.
I like the absolutely psychedelic cup that you used for this.
So to me, this was a really important moment because it means, if we assume there is some kind of ether, we can actually explain what spin 1/2 is in a mechanical way. Whereas there's no explanation. If you don't have an ether or anything, there's no explanation. Spin 1/2 is just abstract, right? Because how can you do it if you don't have, any rotation only has 360-degree repeat, right?
Yeah.
You can't get to 720. You can't do it. But in
your example with the cup, though, you're actually moving the subunits through the entire motion, right? But in your Jello, they're staying still.
Well, on average, you're still. Like my arm, right? I'm not cutting. My arm is still attached to me. I'm not breaking my arm, right? I'm not letting go either, so I'm not cheating. So if I move backwards a little, maybe it's easier to see. I can do this continuously. I'm not letting go. It has rotated twice now, back to the beginning, and I can do it again. I can do this forever. It doesn't change my configuration, right?
Well, it did though, but your arm did move. Like the subunits of your arm moved in space, right?
Oh, but it's not like it's like a harmonic oscillation, just like the transverse wave you talked about for light. The grid points do move away and up and down. In this case, if we were to, if I can do this with two arms too. It actually works with two arms. If we do this, if I were sitting in the elastic solid now, and we put markers everywhere, and we would watch what happens to these grid points, they would actually move in circles.
Yeah. Oh yeah, so I got that. So if this is something that electrons do, right? This motion, whatever electrons are, and electrons are also the outer surface of atoms, right?
Well, they're spherical. They're waves, spherical harmonics, and so they have also these spherical harmonics components. So the wave is pretty complicated, right? It would have to have this spinner part, some wobble motion combined with the spherical harmonics parts, right? I don't know exactly in detail how that would look like, but I would assume if you plot, if you basically visualize the whole electron, each point would have some kind of wobble motion in addition to just the spherical harmonics.
I guess what I'm driving at is it seems like the atom is doing this motion on its surface, in so much as the electron is the outer surface of the atom, or electrons, however you want to chop it up. The atomic surface is doing this spin 1/2 motion that you've demonstrated, as far as I can tell. So if atoms are passing the charge along in the wire, and they're doing this spin 1/2, the charged piece of the surface, which is the electron, is doing this spin 1/2, then wouldn't it stand to reason that what's being passed along is some chain of that motion from one point to the next in the wire? That qualified.
The whole wave stays together and move. The wave packet, the whole wave would move in some fashion, right? If you. It's not like you can't separate.
But it's not like it loses its surface, right? One atom passing charge to the next atom in the wire it doesn't all of a sudden not have a surface anymore, right? It still has, its surface is still doing that spin 1/2 business, or like the complex version of that, and the next one's still doing it.
Yeah, because I mean, so this is what's really interesting about the way that quantum mechanics represents the orbital harmonics and the way that electrons fill orbitals, where it's not that there is some emergent property of the material vibration of the atom as you drive it at higher and higher frequencies. The way that they treat it is that the electron is a little bowling ball that you add onto the surface, and the
Yeah.
surface has this pre-existing shape, which is this orbital. Like the orbital has a shape to it, and it's not present until you add the electron, but then when you add the electron, it can only do the motion of the orbital because the orbital is this platonic harmonic that pre-exists the introduction of the electron, right? Like if you go and read about the nature of the orbitals, they're not like, the orbitals are emergent from the combination of the mass of the atom and the waves that that mass is doing inside of the ether. They're like, these are just the platonic shapes, and when you add electrons, you get to see them. They're imaging the thing that's already there, right?
Well, I think I see this as basically just like the way a violin works or a drum head. So, in a violin, you have, it's very simple, right? You have the ends are attached, so you get, the easiest, the ground level is like this big note, this big wave that goes up, down, and then the next one is you have another note in the middle, so you have then, half the wavelength and so on. And in the drum, you talked about drum head real quick, right? When you put sand on it, the like the lowest vibration is just big up and down, and then you get half, 1/2 going up and down, and then you get quarters and so on. And the electron is just, if you imagine a spherical metal ball and you hit it, right? The way it would vibrate, the lowest vibration, like the s orbital, I guess, would just be like this kind of vibration. And then the next level would be for the p orbital, you would have these lobes. It gets more complicated, right? But that's how you get the spherical harmonics.
But how do you get those harmonics? By adding on an electron, right?
Yeah, like so. This
yeah.
You see what I'm saying?
It's not really a particle. It's just.
It's an excitation. It's another level of drive, is what I'm trying to say. That's where I was at the beginning. Was I'm like, you're overdriving this surface. Is what you're doing. You're driving it into.
Yeah,
right, and you're
vibrational modes to it, right? Like when you have music instrument, you have the lowest tone, and you have another violin playing another tone, and an overtone. So you have multiple modes, basically vibrational modes, and then each mode is an electron, and then you also have to spin one up and down, and so you're adding more frequencies to it, more vibrations into this.
Yeah, like if you treat the atom as an elastic solid that is actually some kind of what's the opposite of rarefaction? Densification? Some kind.
Just treat it as like a material body that's elastic.
It's a material body that is made out of the elastic ether. Yeah. And the thing that gives it its properties is the amount of material that is in motion, which is kind of, I think, a different way of saying what you were talking about, the various waves that make it up. You're like, there's this amount of energy that's contained in this unit, right, which gives it mass. Yeah. And I'm like, okay, so the way that I would translate that into the frame that I use for it is that the amount of material that is in motion there is the thing that offers you mass. It's basically some kind of... the energy comes from the motion. I think both of us are saying the same thing. Right, yeah. Okay. And so then you're stuck with this thing with the electron, which is that if you have the absolute simplest atom, which is a hydrogen, proton and electron, you still have this spin 1/2 motion.
Yeah, both the proton have spin 1/2, actually, and also the electron has spin 1/2.
And so you're stuck with this thing that there's, in order to move up the complexity of the atoms, what you're doing is you're adding like weird motions together. And it seems like it's the weird motions that you're adding that are then producing the even weirder motions that are the orbitals. And all of it comes down to the fact that the atoms are not just little weird field excitations. They have material properties on the basis of what you're calling the elastic ether. There's a material reason that these things all look the way that they look.
I think so, yeah. Mm-hmm.
Yeah. And so I think that we're very much on the same page about that. I'm always stunned by how difficult it is to talk about this stuff because there just isn't a language for it yet. I feel like we're all stuck working out the words, and it's
totally. And there's also misinterpretations, and people have different images when they hear about this. And I just found just a few days ago, I found this paper. It's called Spherical Directivity Resonance Synthesis, which talks about harmonics in acoustics. It talks about spherical harmonics in acoustics. I don't remember the context exactly, but it was all about really technical, but really acoustics, and how you can actually go from one spherical harmonic to another one, the transition, the quantum jump. And they have developed the mathematics and the visualization also, how you can transition from one particular spherical harmonic state to another spherical harmonic state continuously. I'm like, oh my God, that's just like the electron. And I actually implemented the simulation also. So, I think these quantum jumps, quote, are not instant. There must be a way that this is actually happening it takes some time, right? These quantum jumps, in quote, they do take some time. So I really think they're actually spherical harmonics, something vibrating. And when you go, say, from n=1 to n=2 or something like that, there is this transition from this one harmonic state to the next one. And it's not instant. It takes some time. Maybe there's some chaotic in between. And then you end up with the next energy level, as an example.
Mm-hmm.
Absolutely.
And what's funny is it's Einstein got his Nobel Prize, right, for the photoelectric effect, which is kind of sad because at that time people didn't know yet about a lot of things. Like they didn't know yet that electrons have the spherical harmonics, for instance, and how you get from one energy level to the other, right? So
yeah, he may have not come up with a little particle. Like he may not have leaned towards electron particle thing if he'd understood that.
Yeah, because right now there's something called, I don't know if you've heard of a Fermi's golden rule that describes how we can get from one energy level to the next. So how can an electron that's in one energy level, E1, say there's an electromagnetic wave coming in of quote photon, and how is then the electron changed from E1, let's say, to E2, right? People were thinking, these have to be quantized photons, but in fact, there's now something called Fermi's golden rule, which describes this transition probability, and it all has to do with resonance. So it means that the electromagnetic wave can actually be continuous. It's only the detection that's quantized. The absorption of this wave is quantized. And I think it's really important because whenever I mentioned the ether or something like that, people are, hey, it's been proven that light is particles, so that's where the conversation ends, right? So you have to prove that there is a classical model of electromagnetic waves where the photon is really just because of the detection. And
that's the way that antennas work too. Like you got to have an antenna that's properly tuned to receive any particular light, right? It's not like the antenna isn't getting all sorts of light. It's just that it's tuned to receive a particular impetus.
Exactly. Yeah, and there are many examples. Like there's this bridge called Coma Bridge, where there was wind blowing and it started to vibrate and more, and it actually broke the bridge. Or when you have a glass and you sing a tone and you hit the resonant frequency of the glass, you can actually break it, right? And actually, Fermi's golden rule is really works like that. It's you're laughing.
No, I was trying to break some glass in the other room. It didn't work.
You did?
Okay. I don't know.
Or like kids, when you have a kid swing. So basically, the criticism of the the particle thing was in the photoelectric effect is that you need a minimum frequency for it to work. That was one problem they had. And now, and also, imagine when you have a kid swing, right? And the kid wants to jump off at some point. So you can actually, as you start pushing the kid with very little intensity, very little force, but if you hit just the right frequency, it will go higher and higher over time, and until the kid can jump off, right? And of course, the stronger you push, the faster it will reach that height. But if you have the wrong frequency, so if the frequency was, say, once a second, but you only push once every 7 seconds, you go really slowly, well, nothing's going to happen. Doesn't matter how strong you push. If you are totally off, nothing's going to happen. And so that's basically what Fermi's golden rule says. And it's taught in quantum mechanics these days. It's taught in quantum mechanics, and still people talk about particles. Like, if Einstein had known that back then, Fermi's golden rule, I don't think he would have gotten the Nobel Prize for this, because there is an explanation now. You can use classical electromagnetic waves, use Fermi's golden rule that describes that, how likely is it to see that transition? And it depends on the frequency match. So the more the frequency matches the difference, the more likely it happens. And the further off you are, the less likely it's going to happen. And
this reminds me of I was looking like black body radiation is kind of similar to this, because what it is it's like the density of photons of a certain wavelength. And I went down the rabbit hole of like, what is the likelihood of an item being able to emit like a gamma ray photon or something crazy.
Right. Mm-hmm.
And so I started going down the rabbit hole of, I ended up on this, I think it was a physics stack exchange post where some guy was like, okay, so if black body radiation goes off to infinity, so technically if I microwave my food, is there a possibility that it's going to start emitting gamma rays because it gets hot? And in the comments, there's all these people that are basically saying that technically, probabilistically, yes, but in order to make it in order to increase the probability from like 10 to the negative 53 or whatever, you have to heat your food to the degree that it probably won't be food anymore. And you have to have a lot of it. So it's basically the size of the universe. And then maybe.
Okay.
And so, but I think that kind of points to the same thing, which is that we have this like weird probabilistic model of stuff that doesn't really have a physical reflection of what it is we're actually talking about. And so there's both the probability and the quantization of it. And what you're saying is that there is a detection event that is required in order to be able to see the phenomenon.
Which, by the way, happens to be the rearrangement of the surface of the atom. Like, you're talking about an electron transition. You're changing the shape of the atom, much like the Chladni plate. Like, of course it's discrete. Yeah.
Exactly. So there's no reason for the electromagnetic wave to be quantized. I mean, it makes no sense, right? The emission could be quantized. Again, it's the same thing. It's just a reverse process. But also, if you think of, sometimes I think it's ridiculous, because if you think of a radio wave, some radio waves can be like a kilometer long, like a mile. Like, what would a photon even be, right? It just makes no sense to think of as in any kind of particle way. So, and there's this guy, I want to mention him, Sergei Rashkovsky. He has written several papers on this. He has like 90 papers and about 6 or 7 or so on this topic. So he has shown how Fermi's golden rule can explain that light can be classical. He has done the same also for, well, the double slit experiment is really the same thing. It's just, light is just a pure wave. It goes through both slits as a wave. There's really no magic about it. And it's just a detection again, right? The detection event, which is quantized, because again, you have electrons involved in some level that, energy levels are changed. And so now this becomes all the magic is going away then, right? There's nothing weird. The only thing weird about is if you think light is a particle that has to kind of decide which slit to go through. That's the only weirdness. If you get rid of these particles, there's nothing weird anymore about it.
People really love that weird stuff, though. I think that's the problem.
I know. It's kind of cool, yeah.
That's the problem. Yeah, I think that it's really seductive, the weird stuff. I agree that there's enough people who realize the solution that you just pointed out, that the detector is like that's a much less exciting possibility, but unfortunately, probably the more realistic of the two. But until people are interested in realistic explanations for natural phenomenon, as opposed to amazing, outstanding, fun, unreal explanations, the rest of us have kind of an uphill battle, I feel like.
Yeah, and actually Schrödinger, he was a big proponent, right, of the wave interpretation. So he said a number of things. He said, for instance, that material points consist of or are nothing but wave systems. He said that in 1926. And he also was really unhappy about the probabilistic interpretation. If you have heard that quote in 1952, he said, quote, "Let me say at the outset, I am opposing the basic views from when Max Born put forward his probability interpretation." And he was really upset about it. So he was really sorry that he was ever involved in this.
Yeah, I've heard that the Schrodinger's cat experiment was intended to show the absurdity of this.
I know, it's a joke. It was a joke. He was trying to make it clear how absurd it is. And now people take it as an example. I mean, I feel so bad for Schrödinger. Yeah, it was actually a joke,
Yeah.
And there's another quote I like. I'm not sure, I couldn't find the source, but I've seen it in many places. And he, at least it's quoted as him saying it, that what we observe as material bodies and forces are nothing but shapes and variations in the structure of space. This sounds to me exactly like the elastic solid, right? It's just basically the matter is nothing but shapes and variations in the structure of space. So I think that's kind of nice. It kind of sums it up in a way.
Yeah, I like that a lot. Shiloh, what do you think?
I want to keep talking to you. I think we should put a pin in it for today. But I'm not done with this topic, and I haven't found anybody else to talk about it with as well as you. You gave us a number of names of people to reach out to, and I think we should do that for sure. And I know we haven't made it through all of your work, but it might be good to get this one out and then circle back and try to pick up some of the patches that we left behind. Like, I think there's a whole conversation to be had about the isotropic versus anisotropic organization of these subunits and how that might relate to stiffness or imply different forms of stiffness, if we're going to go with stiffness being the informing feature. But it's probably too big of a conversation to just try to like slam in here at the end. So I don't know if you'd be down to come back in a couple months or whatever.
Yeah, there are other topics like there's whole EPR Bell thing, and actually there's also implication on the Big Bang Theory. I know it sounds I don't know if you have 5 minutes or something just to mention, even though I know it seems unrelated at the surface, but it's actually quite related, because if just even ignoring all the problems we're seeing with old galaxies and all that, like just not even just completely ignoring that, right? We are saying that space is expanding, and because of that, the light wave is being stretched. That's what the essence is, right? There's a redshift because space is expanding. Now, at the same time, they're saying there's no space, right? There's no medium. there's no space. So, well, if light is not a wave in a medium, then how can it even be stretched? So that's my first question, right? That's like a logical inconsistency. I mean, either you have a medium, if you don't have a medium, and light is just its own self-promoting thing, how would it be affected by the stretching of space? And how can it even stretch if there is no space? That makes no sense, right? So then you could say, well, actually, then the medium kind of shows Big Bang Theory, right? So basically he says, well, if there is a medium and light is a wave of that medium, then yeah, it makes sense that if you stretch it, of course, yeah, then the light would stretch, right? That makes sense. But the problem is, then matter would also stretch, because matter is also a wave of that medium. It would stretch the same way. And then so relative to each other, there will never be a difference. We could never tell. Like we could just stretch everything twice the size. It would all be the same relative to each other, same relative distances.
I think they say that it's empty space that's stretching. Like the amount, but I'm not saying that to be like, Chantal, you're wrong. I'm saying that say that the absurdity of it is that I think that they recognize the point that you make, that if space itself is stretching, then there would be no difference. And so the way that they deal with that is they say, oh, no. It's not the objects that are stretching too. It's just the intervening distances.
Okay.
That's what's crazy.
So fine. Now we can go with that. So if we add some kind of like add space, well, then why would light get stretched then?
Yeah, no, I totally agree.
I'd say you don't even need a Big Bang to apply this elastic dissipation to the reddening of light. I mean, I assume we're talking about the reddening of light with all of this.
I'm just talking about that part because, and also,
Yeah.
I mean, the thing is, there's so many reasons why light could be red.
There's many elastic reasons why light could be red.
Yeah,
that's
like
what I'm
mass
saying.
drag effect, that kind of thing. You know,
Just
I mean,
just dissipation, just
yeah,
literally
just over time,
friction.
billions of years, you lose a tiny amount of energy. Right? I mean, it's and it's funny. That's how I actually started this whole thing. Is really when I asked a simple naive question on a forum, because we know that light can be read because of the Doppler effect, or it could be stretching of space, or it could be gravitational. So I asked a simple question: how do we know that 100% is space expansion and not maybe it's 80%, 10%, 10%? And then I was, you're a heretic, basically, right? I'm like, well, that's a serious question. How do we know it's all space expansion? And I realized there's no answer, right? Nobody know. They just assume it. It's just. So anyway, that's kind of.
There's so many of those. It's quite interesting. I mean, we had the same thing. I mean, we got stuck on this too because we asked a very innocent question what charge was, and here we are 10 years later.
Almost done with the book.
Pissing people off all the time, yeah.
But I think that everybody... Oh, go ahead.
Oh, no, okay. Sorry, I didn't want to... I know you're almost out of time, but there's another really, really simple sounding thing called, the Doppler effect of light. You would think this is so innocent, so harmless, and so easy, because we know how it works for air and sound, right? I mean, there's a vibration, like in a car emitting a sound, it's transmitting the frequency into the air molecules. The air molecules, it propagates, and then a receiver receives that vibration. So the Doppler effect is totally simple to explain. Because if you move towards relative to the air, for instance, the receiver would receive the vibrations more quickly, so there's a shift and so on. It's very, very easy. But for light, if you have an elastic solid, it's the same thing. Star emitting some light, the vibration, the transverse is in the medium. It is actually propagating in the medium. And relative, if there's a receiver relative to the medium moving towards it, you will have an increased frequency. And so very totally trivial. But now, if someone claims, well, there is no medium, then, imagine there's a star exploding 10 billion years ago, and the light was emitted at a certain frequency. Well, what kind of frequency relative to what, If there's no medium, what's the frequency? There's no mediums. There's no what's carrying the frequency? No. And then later, when we received that photon in quote, the star was long gone, right? So how do we get this relative velocity, this relative frequency between Earth and that long gone star? If there's no medium, there's no mechanism.
Yeah.
It's really crazy. They asked this naive question on the forum too. There's no answer. They cannot answer it.
Well, a wave doesn't make sense without something to wave.
Exactly. It's so ridiculous though, because the Doppler effect is so easy, right? They would. I had a friend and he told me, well, you have to draw a space-time diagram, sure, but but the light was emitted 10 billion years ago. It must somehow carry that information to the present. How does it do that? And it's you get all into this whole magic. Well, there's no light until you actually detect it, and it's just it's just crazy, right?
I mean, I do think that the specifics, and this is why I'm dead serious. I think we should continue this conversation because I have a lot more that I would want to unpack here, because the specifics of the wave during electromagnetic radiation are actually really interesting, and I think that they really stumped the progenitors of a lot of this theory. I think when it comes to why the ether died, a big part of that was that they couldn't come up with a material who would oscillate in a way that would change the polarity of the electricity at the other end of the antenna, right? So what is the primary readouts of, I love antennas because they're really easy to study. We know exactly electrically what's happening at either end. And you have essentially this oscillation of polarity in the conductor at either end, essentially. So the transmission is the change in polarity, i.e. the charge states of the partner at either end of the light transaction. And so you have to have a model for charge, or you can't possibly understand what the medium is conveying in terms of the impulse to at either end, right? So we have to really, really be on the same page about what charge is.
About this.
You see what I'm saying? In order to
Totally.
really say what that transverse oscillation is, we have to understand how it's oscillating at either end and what the material representation of that is, and then we can understand how the medium can convey it. I mean, it obviously has to be an elastic medium for sure, but the specific structural aspects of that are really, really important because they're going to allow us to do the feat of changing the charge at either end, of changing the surface motion of the atom in a very particular way. And the particulars are what it's all about at the end of the day. I don't know, something to think about. Maybe we can circle back on this later.
Yeah, that's great. I like the idea of thinking more. There are so many open problems, so that's a great one.
Yeah, I think that this is just something that we spend so much time thinking about, and we have had at this point probably almost 200 conversations with physicists of all stripes. Right, because we're at 370 something episodes of the podcast. About half of our episodes are physics conversations, and the number
they all sort of end up here eventually.
well, where they usually end up is Shiloh and I are talking to some kind of mathematical, theoretical quantum physicist, and we're like, hey, don't you think that fields are an insufficient way of explaining why something happens? And they treat us like we're just the dumbest dumbs that have ever dumbed in the entire world.
Oh, that's rude, yeah.
Well, no, it's not even like, it's not, they're not trying to do it. I think that they're just so
unaccustomed to thinking in terms of material actors, right?
Yes, but there's such a logical contradiction. By definition, if a field is abstract, it can't influence reality. That's the pure definition of the word. So I'm not saying the field maps one-to-one, but there must be some underlying real thing. Otherwise, how could a mathematical formula affect something real? That makes no sense. Just based on the word, it just makes no sense.
I think that the field might actually map fairly accurately. Like, I think that some of the things that Shiloh and I have been trying to figure out is if you take the mathematics of quantum physics and quantum mechanics as a given, and quantum field theory and electrodynamics and everything else, if they actually are accurate measurements and accurate readouts of what's actually happening, and then you can go and you can understand the system that they're using to measure so that you can figure out what you're saying about the photoelectric effect, which is, okay, is this just a measurement problem? Is this just the fact of how our detector is set up? Or is this a true, like, if you can deconvolve all of that, then where we're sitting is that we actually have the greatest trove of information that anyone in history has ever had about fundamental physics, and almost nobody except for a handful of people who are sitting there and are like, that's really interesting. What if it actually meant something?
I know, we should map it back to the ether somehow. Maybe, I think the different fields are just different, maybe viewpoints of the ether. Like one field just looks at the transverse waves of light, and another field looks at the, the electron aspect of it. So it's just looking at different maybe frequencies or different, sizes, but it's really the same thing. It's just like when you have waves, of course, you can always separate waves out, right? You can add waves and subtract them. So it's like a lens. Each field is like looking at one aspect of the wave, and like a filter. I think that's pretty much it. And the fields are really just, I think they can be mapped to the elastic ether. So
yeah, I have so many more, like Shiloh said, we have so many more questions. It'd be really cool the next time you come back if we had a list of animations that we could show.
Oh,
and then basically walk through the work that you
simulations.
Yeah.
And if you want to send me a few of those questions, I wrote down the antenna charge thing. Then I can think about it and also maybe write a simulation,
Ooh.
Well, I think people are going to love this. And this is our favorite topic on Earth. So I often tell people at the end of these podcasts, I'm like, hey, we should do another one of these. But I'm like, really want to do another one of these conversations because I feel like there's so much more to talk about. And we've been talking about this for 3 hours, and I still have pieces of it that I would love to run by you and try to get on the same page about.
I feel like we're just getting started. I feel like the first 2.5 hours were us figuring out where we were, if we were on the same page or not, and like figuring out the definition of terms and stuff. And now I think that we have enough of a map that we can really make some progress.
Yeah. Anyways, I would just if you think it would be if it's worthwhile to you, it'd be wonderful to get you back here as soon as possible.
Yeah, totally.
So we can talk
it also
some more.
Motivates me to think more about this and write more simulations. Yeah.
Heck yeah.
What do you do in your day job?
I develop algorithms, complex algorithms for actually forensics. The thing is, because I think I make mistakes every single day, okay, I have to debug really complicated code, like hundreds of thousands of lines. So I'm really persistent. I don't give up easily. And I know I make mistakes and I figure it out. Like I have to be really careful, not to make mistakes. And so it's just the kind of thinking, and also I need to understand something at the deepest level. Otherwise I couldn't write the code for it. So that helps me to think about these things as well, And I see
awesome.
bugs, like I see red flags when when something is illogical, doesn't work. I just kind of see, like in code, I can see errors right away. So this is sort of kind of a little bit, related, I think.
I think so. That's really cool. All right, well, let's do it again, Chantal.
Sounds good.
Awesome.
Yeah, thank you so
Nice
much.
talking to you. Bye-bye.
Yeah. Bye, everybody.
Have a good rest of your night.